Hello, my name is Jiwoo and I am PhD student in Seoul National University. I would like to talk about my research, which is HPC Workload Characterization using feature selection and clustering. The content of my presentation is as follows. I will first introduce the background of our work, including the dataset we used. Then I will explain the pre-processing steps we applied to our data. I will also explain the feature selection and clustering models we used to cluster the data. We evaluated the cluster results using several cluster validity metrics, and based on this evaluation, we characterized the optimal cluster result. So there are several high-performance computing systems we can use, and this figure is one of the popular HPC systems, core system in NERSC. The applications run their jobs on HPC systems to exploit efficient storage management and high-performance computation the system provides. In order to get higher performance, the system provides some tunable parameters to the users, such as the number of compute nodes, the stripe count, or the stripe size. Users can tell the system how much resource they want to use when they submit their jobs. However, the problem is that the users are not that familiar with using these parameters. From the past 4 months dataset from October 2017 to January 2018, we found out that most of the users use just the default configurations the system provides, or the maximum available resource, hoping to get the higher performance. So this left side of the figure shows the stripe size the users use. Total 23,765 jobs are run with Core default stripe size, which is 1 MB. Also, most of the users just use the Core maximum start count of 248, so they're hoping to get the higher performance. Since the HPC applications characteristics are so diverse, they mostly do not meet the proper I/O demands. The I/O characteristics for each applications are so different, and also the performance can differ depending on the HPC system. So it is necessary to simplify the use of system configurations, providing the proper existing environment for different workloads. Therefore, we need to understand the different I/O demands of HPC applications in order to provide the necessary I/O configurations or to analyze the reason for their performance. In order to do that, we clustered the HPC workloads based on their I/O behaviors using the real I/O log. So we used the real-world user log data run on Core system from October 2017 to January 2018. So we used total 4 months Darshan log data. The Darshan I/O profiling tool is used to capture the I/O behaviors of applications run on Core system. It also interacts with Slum workload manager to make the Darshan log. We also use the parser to extract the meaningful information from both Darshan and lost monitoring tool utilities. So total 78 features are obtained from the parser. From those features, the I/O throughput is our target variable. So in this paper, we categorized the HPC applications based on their I/O behaviors. We can change this target variable, but we decided to categorize based on the I/O performance since we are using the features extracted from the I/O profiling tool, which is Darshan. There are several data pre-processing steps we have to do before applying the machine learning algorithms. So we first drop the user logs with less than 1 GB I/O, since they cannot precisely capture the right relationship between features and the target variable. Also, we set the data having negative values to 0, since they are the error data and they cannot be applied with machine learning algorithms we used. Also, because the features with the constant value are not meaningful at all when we apply the machine learning algorithms, we just eliminated all the features with 0 variance. And our features are highly related to each other. Like for example, the feature of read less than 1 kilobytes and read more than 1 kilobytes are two complementary features. So we eliminated the features having more than 0.8 correlated value with other features. It is to reduce the redundancy among the results of feature selection algorithms. Finally, all the feature data is normalized to range from 0 to 1 so that the features can have same scale and weight when calculated by feature selection methods. After these data preprocessing steps, this figure shows the top 20 mostly executed programs. So we use total 62,946 entries run from 353 different applications left after the preprocessing step. Before applying the clustering algorithms directly to the dataset, it is necessary to reduce the computation dimension. So selecting the right features that can best represent the data is necessary. We used total 5 different feature selection methods to select these representative features. The first 4 algorithms we used are very popular feature selection methods. We used mutual information regression, F regression, decision tree, and extra tree algorithms. All these 4 selects the features with different algorithms, and they have different impact on clustering models, which we are going to do in the next part. And in this paper, we also implemented the new feature selection method just for our dataset, which is min-max mutual information. This is because of the characteristic of our dataset, which is that most of the features are very highly related to each other. In order to further reduce the redundancy of the selected features, we implemented this new feature selection algorithm. So in order to apply the min-max mutual information algorithm, the data preprocessing step of removing the features that are highly correlated to others is not applied beforehand. Then it works in a way that it selects features that are less correlated to each other. So the first feature that has highest correlation value with right weight total, which is the target value, is selected, and then this process is repeated until the desired number of features are selected. And these are the results of various feature selection methods. Since the preprocessing step of min-max mutual information is different from the others, the selected features may not be included in the rest of the results. And we are going to use these feature selection results and evaluate the clustering results from these using each of these 5 sets of features in the next section. By using the selected target relevant features, we evaluated 3 clustering models in our work, which are K-means, GMM, and word linkage clustering. The clustering models run based on the previous 5 different feature set results. And in order to evaluate the cluster results, we used these 2 cluster validity metrics and also combined them into combined score metric. Good clustering tries to maximize the inter-cluster variance and minimize the inner cluster variance. These DVI and silhouette score metric weight those variance in different algorithms. For DVI, the lower score means the better cluster quality, and for silhouette, on the contrary, the higher score represents the better clustering. Since combined score is defined as silhouette score divided by DVI score, the good clustering results in higher combined score. For the performance evaluation, we took 2 steps. We first select the best clustering method among the 3 models we used. We first used the feature selected from min-max mutual information since it is the most suitable feature selection method for our dataset characteristic. So every features in the min-max mutual information result are considerably correlated to each other. Using these features, we vary the number of clusters from 3 to 20 and evaluate the cluster performance with three cluster validity metrics, which is DBI silhouette and combined score. So this graph shows the score results from DBI silhouette and combined score. And note that the lower the DBI score and higher the silhouette score, and also the higher the combined score, indicate the better the cluster quality. The graph shows that k-means and word linkage clustering are very similar in cluster scores, while GMM shows slightly different trend compared to other two methods. Both k-means and word linkage show the best clustering performance, especially when the number of clusters is 3. Since k-means and word linkage are so similar in clustering performance, we can say that the best clustering method is k-means clustering. And we also evaluate the features selected from 5 different feature selection methods. In order to figure out the impact each feature set has on k-means clustering method, we again run the cluster validity metrics to evaluate the cluster performance. So these three figures depict the results of DBI, silhouette, and combined score from the k-means clustering result, each using the 5 different feature sets. Likewise to the previous slide, the lower the DBI score and higher the silhouette and combined score means the better the cluster quality. And the graph shows that on every case, except for the score of 5 clusters in DBI, the min-max mutual information scores the best. From these results, we can conclude that the clustering result using features selected from min-max mutual information shows the highest cluster performance. So far, we have selected best feature selection method and best clustering method from the selected features using the cluster performance evaluation metric. And this table depicts the average value of 3 clusters on some of the features. After we get these average values of every feature, the clusters can be characterized by determining the features that have dominant value on each cluster. So for every feature, we select the cluster having the highest average feature value. Then in order to assert that the cluster really has high tendency of this feature, we figure out whether the cluster has more than twice as high a feature value than that of the other features. These 3 red bars represents that the cluster has characteristic related to the feature, since it has dominant value compared to the others. So this table shows all the features, with the black box representing that the cluster has characteristic related to the corresponding feature. For example, for the first feature, which is the consecutive write percentage, it means the workloads included in cluster index 0, which is cluster 1, have high percentage of consecutive write operations. Overall, we can cluster the HPC applications with following characteristics when clustered by 3. So for the first cluster, the workloads in the first cluster tend to issue less than 1 megabyte size read and write operations compared to the other clusters. In fact, many of the read and write operations operate on less than 1 kilobyte blocks, and a significant amount of I/O operations are on STD-IO units, which are typically very slow. Furthermore, the workloads in this cluster also use a few hundred MPI ranks. Overall, the average I/O throughput for cluster 1 is only a few megabytes per second. For the second cluster, the workloads in this cluster tend to issue more than 1 megabyte size read and write operations. Especially, all the workloads issuing more than 1 megabyte read operations are included in this cluster. Also, the total bytes written to the file is highest among the 3 clusters, which also means that there are lots of I/O operations during the processing time. These workloads are likely to use 8 megabytes stripe size in average, which is 8 times more than the current default configuration, which is 1 megabyte stripe size. The workloads use about 1000 MPI ranks each time and does not spend too much time in MPI I/O. We can suspect that using only a modest number of cores and not using the MPI I/O for parallel I/O operations might be the reason for the workloads to achieve the high I/O throughput. And for the last cluster, the workloads in this cluster use more than 70,000 MPI ranks on average, which are the largest parallel jobs in our dataset. When compared to the other clusters, the workloads in this cluster use 62 times more processors on average. They also issue a large number of I/O requests, including the metadata operations such as open, seek, or stat requests. On average, each MPI rank issues nearly 500 open requests, which is the high number. The block sizes of read and write operations are less than 1 megabyte, which is lower than those in the second cluster. From our analysis, we can assume that the workloads in this cluster deploy lots of processors for higher parallelism to achieve the highest I/O throughput among the three clusters. So this is the summary of our work. We extracted the features highly related to the I/O performance. And specifically, we implemented the new feature selection algorithm, which is min-max mutual information, in order to get the meaningful information from the real HPC workload data. We clustered the HPC applications and evaluated with cluster validity score. And from the result, we could identify the meaningful clusters from the large set of application logs. And for our future work from the clustering results, we are going to provide the guidance to applications in each cluster, the detailed guidance to improve their performance. This is the end of my presentation, and thank you for listening. Thank you.